Okay, guys, we'll start by looking at these reactions of amides. I do have a handout. I know you wanted one of those today. So I thought I'd give you one. Okay, guys, top of the hour, we'll get started. The handout going around is IR. Spectroscopy for test 3 will not be a comprehensive spec problem. Instead, it will be just IR. We'll be reviewing IR acid derivative functional groups. For test 4, we will go back to a comprehensive spec problem. This handout here is reviewing a little bit of IR, a little bit more than review. It's also focusing in on the carbonyl position in the IR. Your acid derivatives which contain a carbonyl the peak position for the carbonyl in the IR varies depending on which acid derivative you're looking at. And that's what this looks at. Please look over this handout. We'll see what kind of questions come up. And so like on next Monday, please be ready to ask questions about this handout. The problems in the workbook, on your test 3 material. Okay, guys, let's look at the amides. We left off right here. This is called benzoyl chloride. It's the acid chloride of benzoic acid. React this with 2 equivalents of methylamine. What are we going to get? Methylamine is a nucleophile. We're going to do an ACL substitution to replace the chlorine. We have a mechanism. Okay, it's addition elimination. You don't directly displace the chlorine. At some point, you will look to produce HCl because you'll lose an H from the nitrogen. Cl. HCl will mess up your nucleophile, so you have to include an extra equivalent to take care of that. Product here will be the secondary amide plus the methylamine hydrochloride. Any questions about that one? How are we doing on that one? Okay. Now here we have the acid chloride on the left and the amine on the line. It doesn't matter, they're both in the same flask. You can put the amine over on the left with the acid chloride on the line. In this case, the amine is sort of a smaller molecule. Methylamine, ammonia, small amines. In this case, the amine is a larger molecule. And then this is sort of a smaller reagent. No difference. We still have a nucleophilic amine and acid chloride. Nucleophiles attack here. Where's the nucleophile at? The amine. Okay. What are we going to get? I need to draw out the green because we have two substituents. Ugly bond angle. Let me erase this one up here. Put the H up, put the carbonyl down, and this is going to be a methyl. Basically, there's your acid chloride, right, under my hand Cl, but instead, now the amine is under my hand. And the nitrogen loses an H. You can show HCl being formed. What's the purpose of the triethylamine? To react with that HCl, so this amine will not react with it. And so you will also get triethylamine hydrochloride. We can maybe show that like that. Of course, it's triethylamine where the nitrogen is bonded to an H, that's a plus charge, and a Cl minus. So in this case, we use not two equivalents of the amine, but we added in a sacrificial amine to take care of the HCl. Why did we use two equivalents of amine up there, but not down here? Anybody? Cassandra?
One of them's going to be more expensive than the other.
Yes, methylamine is very cheap. Just use another equivalent to act as a base. Down here, this is probably not that cheap. Or maybe you can't even buy this and it took you a year to make this. If it takes you a year to make it, do you want to use half of your compound just to serve as a base? No. So you put in some other base that's cheaper. Now triethylamine won't react with the acid chloride to give a product. There's a variety of bases that can be used as sacrificial bases that won't react with acid chloride. Triethylamine. What was used in lab? It's actually, I had to modify the procedure. What bases did we substitute in? We made amide in lab. Not acetamide, but benzamide from an acid chloride. Nobody made benzamide in lab?
I did. Yeah, but it was like for 3 weeks.
Dapco was a base. Yeah. 2,6-lutadine? Yes. 2,6-lutadine is, what is that? That's pyridine. You put two methyls here, and it's called 2,6-dimethyl pyridine, also called 2,6-lutadine. Not sure where lutadine name came from. The methyls make it less toxic because they can be oxidized in the body. We talked about like toluene. Actually, 2,6-lutadine is I hate to tell you this. It's a food additive. If you look it up, it's used in some foods. It's not that toxic. But don't be eating it in the lab, okay? Please. But it's safer than pyridine without the methyls. Dapco is here, and then you got this 2-carbon bridge. So each nitrogen is trivalent. What you'll see is neither one of these nitrogens has an H to lose. And so they can't make a fourth bond and make an amide. So these are some bases that can be used. Triethylamine is very common. I went away from using triethylamine in lab because it's very smelly. It's more volatile than this guy. This is also smelly, but it's not as volatile, so it doesn't get in the air as quickly. Okay, so sacrificial amines can be used to consume the HCl, especially when your amine, like the aminofluorine. Do you want to use half of it in lab just to serve as base?
No.
No. Right? And then throw in the waste container with protonated? No, that's a waste of your good amine that you spent time making. Okay, so ammonia, very cheap. Methylamine, pretty cheap. Okay, chlorides are great intermediates. They're key intermediates for making other acid derivatives. The actual acid, it's very difficult to make other acid derivatives in a lot of cases, especially when you use a strong nucleophile. Reacting with a carboxylic acid with a strong nucleophile is not going to give you an acyl substitution. Instead, the strong nucleophile will act as a base and take the acidic H. When it takes the acidic H, what do you get? The carboxylate. The carboxylate, because it's an anion, is unreacted towards nucleophiles typically. So once you do this, game over. Remember Donkey Kong whenever you got like killed? Game over, right? So you can't just react an amine with this and expect the amine to substitute out the OH. The amine will take the H. You can't react it with a Grignard reagent like we'll do down the road with some other things. Just take the H. Game over. But the acid chloride, on the other hand, reacting with a strong nucleophile, it doesn't have an acidic H. So instead, the nucleophile does what you want. Addition. Okay, and then you can come back down and do your substitution. That's why converting your acid to the acid chloride using what? I know chloride is a great first step. Now you can do anything with this. Okay. And what were we just doing here? Chemistry of acid chloride. You can do so much more with it. That's just some of the chemistry. Let's look at chemistry of acid anhydrides. What is an anhydride? An anhydride is something that apparently has lost water. Sound reasonable? We'll see why it's called an anhydride. First, let's look at this structure. An anhydride has an oxygen bonded to two carbonyls. And typically, coming off the carbonyls are just plain R groups, or an H. But it would not be another heteroatom coming off the sides. You can have a symmetrical anhydride where the two R groups are the same, both methyls. And that's acetic anhydride, abbreviated AC2O. What does AC stand for? Acetate. Acetate? Not acetate. Acetate is ACO. What does AC stand for? Acyl. Stands for that right there. That's your acyl. If you want acetate, what do you have to add here? An O, right? So it's acyl O. That's acetate, minus. Okay? So this is an oxygen with two acyl groups. So it's an oxygen with acyl there and acyl there. So that's how it's abbreviated. And many of you use acetic anhydride in lab, yeah? To make an acetamide. Remember, functional group with one carbon. Well, if it's an acid, it's actually two carbons. It's a methyl coming off. It's really always two carbons, but it's just a methyl. And then the other carbon is part of the functional group. That's all, the slang for all that is always acetyl. Like acetonitrile, acetic acid, acetyl chloride, acetic anhydride, okay? This would be called a mixed anhydride, where the two R groups are different. Or you could call it a non-symmetrical anhydride. Mixed anhydride is a pretty common term. Okay, how do you make anhydrides? You make them from carboxylic acids. All acid derivatives are made from carboxylic acids. We've already seen one way. Look back at Roman numeral 2c. What do we make over there? It's over here at the bottom of this page, right here. We made this mixed anhydride. Took an acid, dragged it with a base, and then we got the oxygen to add to replace the Cl. So under my hand used to be a Cl, but now the oxygen nucleophile is under my hand. Okay? I'll say this again, but let me say it, I think, the first time. Most of this chemistry is just going to cycle back around on itself. Okay? As we do this, you've got to realize that you don't learn a million different things. Learn the fundamental chemistry, and then you can just work this out. And then you say, it is an anhydride. Think mechanistically. Okay? As we move forward here in test 4, you've got to keep thinking general. Even more so. And then when you then be ready to see anything, it's just like math. Okay? I said this a good bit in Organic 1. When you take math, you don't memorize every answer, do you? 56 times 13. What is it, Joseph? You didn't memorize that one? Why not? How are you going to get it right on the test?
Calculator.
You don't have a calculator. How are you going to get it right?
Write it down.
You know a mechanism for working it out?
Yeah.
Okay, that's how you gotta approach these reactions. And at the same time, whenever you see something weird on a test, you don't freak out. You just, well, I do this and I do that. Here's the problem. Okay? I got to encourage you to think like that. Especially here. This stuff just cycles all. If you try to just memorize it, it's just going to be like, well, did we just do that? Yeah. We're just going around in circles a good bit. So we've already done that. Okay. Another way to make anhydrides is by thermal or chemical dehydration of a carboxylic acid. Now, it actually takes two equivalents. When I say a carboxylic acid, I don't mean one molecule of a carboxylic acid. I mean a carboxylic acid that's in a beaker. Gazillions of molecules. But if you take two equivalents of a carboxylic acid and heat the bejeebies out of it, pretty high temperature, you'll get the anhydride plus water. You'll drive water out of this. And usually the water, because it's high temperature, it comes out as steam. And the steam can be driven away. Now, if you take this formula and remove water, what are you left with? You're left with that formula. So you're dehydrating the carboxylic acid to make, what's it called? Why is it called an anhydride? Because you've driven off the water. Okay? Mechanistically, this is probably like a Fischer esterification. Except it's probably one acid protonates another, then one acid does a substitution, and you kick off the water. You can do that mechanism yourself. It should be very doable with what we've already done. The only problem is it's really not a strong acid. So whenever we do the Fischer esterification, it does require a strong acid. This is very high heat, like 200, 300 degrees. And a lot of times when we do super high heat, a lot of the mechanism requirements are not quite as required. Okay, you typically only want to make an anhydride this way. You typically only want to make a symmetrical anhydride this way. If you try to make a mixed anhydride this way, by reacting two different acids, you're going to get a mess. You might say, hey, these two react together to give this mixed anhydride. Well, yeah, that's all fine and dandy, but two of these could also react together to give that anhydride, and two of those could also react together to give that anhydride. If you try to make a mixed anhydride, you're going to get three products. So the thermal, this is thermal. You can also do chemical dehydration. There are some drying reagents, dehydrating reagents that can be used here. I'm not going to mention any, but that's what I mean by chemical dehydration. This would be a thermal dehydration, only for symmetrical anhydrases. Cyclic anhydrides, very common. If you take a diacid and heat the bejeebies out of it, you can drive off water and get these cyclic anhydrides. Okay, anhydrides. I bet that if I had a quiz right now and you had to draw a cyclic anhydride, 3/4 of you would not be able to draw it correctly. Okay? So make sure you know what your functional group looks like. You got to sit down, okay? You can't just look at it once and say, okay, that's an anhydride. You actually have to start writing. You know, there's studies. You can think about something, you learn it. If you write it, you learn it even better. That's proven studies, right? So when you sit down, don't just assume you know what something is. Write it out. But I've seen it all the time. 3/4 of you just, that's not an anhydride. What is an anhydride? Don't answer me. Make sure you know what it is. All right, we've already said what it is. Okay. Now, this is succinic acid. It's a diacid. That would be called succinic anhydride. By the way, y'all remember when we did Diels-Alder in Organic 1? Those that had me? Did we do this? Butadiene sulfone? What did we react it with?
Anhydride.
That was maleic anhydride. Maleic anhydride has a double bond between the two carbons. But we used an anhydride back in Organic 1. And I think in the lab it said that that's an anhydride. Yes, it says the chemistry of anhydrides, along with other common carbonyl-containing functional groups, is covered in Organic 2. Well, that's where we are now, right? So you've actually used an anhydride if you had me in Organic 1. We didn't do any well, because it had the double bond, we used it as a Diels-Alder dienophile. So we really didn't do carbonyl chemistry. We used the double bond part of it. Okay, reactions of anhydrides. Okay, when you see an anhydride, only one carbonyl is what you attack. Okay? The other oxygen and carbonyl is going to be your leaving group. So that's like a big chlorine there. Okay? For your acid chloride. So the nucleophile, of course, come in here, electrons up. When you come back down, you kick off this oxygen, and so there's your leaving group. Now, if the anhydride is symmetrical, both carbonyls are the same, so it doesn't matter which one you attack. If it's a mixed anhydride, we're going to have to decide which carbonyl we attack. Because you don't always attack the left one on the board. Right? That's just, could have attacked this one, and that could have been the leaving group. But it's really no difference if you understand that one portion is the leaving group, just like the chlorine being a leaving group from acid chloride. We'll do some reactions below. Before, let me point this out. Anhydrides are not as efficient as your acid chlorides. Let me show you why. For example, if you have carboxylic acid, 1 mole, and you want to make an amide, you would first convert this to the acid chloride, and you'd still have 1 mole. That means 1 mole means what? What's that? About 10,000 molecules? How many molecules is that? Oh, that's a big number. Okay. 1 mole of this, you have the same number of those molecules. Okay? Makes sense. You're just switching out the chlorine. Now react this with ammonia, we can get 1 mole of our amide. Okay? But let's look at if we made the anhydride. 1 mole of this would give how many moles of the anhydride? Only a half, because it takes 2 of these to make 1 of these. Now when you react this half a mole with the ammonia, which by the way, this will attack, electrons up, back down, kick that off, you'll have the nitrogen there, and then the other ammonia will take the H, and you'll end up with this. But that's only going to give half a mole of the amide. So the other portion here will be essentially your base. I'm sorry, it's not the base, it's the conjugate. It's the conjugate base of the acid group. So again, half of your original acid served as a leaving group, and it's just wasted. So that's the problem with anhydrides, is half of your original acid is wasted as a leaving group. What's the benefit of anhydrides? Well, they're less reactive than acid chlorides. They're still reactive enough to do the chemistry, okay? But they're not so reactive that they're so sensitive to water. See, acid chlorides, they are so sensitive to water that you just open them up, you let some atmosphere get in there, and there's water in the atmosphere, it starts reacting with them. On the other hand, an anhydride, you get some moisture in there from the atmosphere, it's just not enough to do anything. Unless you start actually adding water into it, it's just not going to react there. So it lasts longer, it's more easily stored, etc. If you react these with water from the atmosphere, you'll get the acid plus what? If you react this with water, you get the acid plus what? HCl. So when these are exposed to the atmosphere and it's a little bit of water, they start generating HCl. A lot of times when you open up an acid chloride, a little gas comes out. HCl gas. Because last time you opened it up, some atmosphere went in, it was wet. So anhydrides are more stable. Also, something like acetic anhydride, you can buy a big old jug of it for like 20 bucks. Where acetyl chloride is more expensive. One reason it's more expensive is because the chemical company has to take more precautions with the acetyl chloride. Okay? So it's not as efficient, but there are reasons when you would want to use such a reagent. After we do some reactions below, I'll show you some reagents where you have to use anhydride. Okay, let's do some reactions. Why don't you guys on the left do the first one, and you guys on my right do the second. second one, we will see reactivity of a cyclic anhydride. This is what I talked about earlier. Who cares if it's cyclic? If you think mechanistically, it's no different. So just because it's cyclic, it's not like it's going to be so radically different. It's still the same mechanism. You just do your mechanism, what reacts with what, and then you, well, that's the final product. I would look to go to show a neutral product with no charges at all, if you can. Okay, well that's acetic anhydride, right? You need to know that, that's trifluamine. Here's your nucleophile. Electrons add, electrons up. I'm just going to call this phenyl, boom, boom. So this is now bonding to the carbon, electrons up. What else is on that carbon? A methyl, oxygen, plus charge there. Is that the bond we just made by nucleophilic addition to carbonyl? Doesn't matter which carbonyl you add to, because it's symmetrical. We can do proton transfer in a mechanism, okay? The reason lots of times books don't do that is because they just don't want to draw into the structure. Typically you may see just these electrons come back down, and we kick off the other thing. That's going to give we now have double bond to oxygen. What else is on this carbon? A methyl. Plus the leading group, which is actually acetate. What am I missing? Good, plus charge. You can't have a minus without a plus. At least somewhere on the board. If it wasn't here, then there's got to be some like potassium or something somewhere. And now this, do we include any base?
Yeah, we're in the triathlon.
Well, trifluamine. I can have that take the H. In the end, the final product is that there. Something takes the H. We can have that take the H and we can make acetic acid. Or we can have trifluamine take the H. And we make trifluamine acetate. Or you can make acetic acid first and then have trifluamine take the H from acetic acid and you make trifluamine acetate that way. Acetic acid is strong enough to protonate this amine, so you want to include a base to take care of the acetic acid that would otherwise be formed. In the end, what do we make? We start with an amine. What do we now have? An amide. Yeah, carboxamide, an amide. A unique name for this amide. An amide that is. See, this can be considered an acetic acid derivative. Because if this goes back to the acid here, that means you make an OH here. What would that be? Acetic acid. It's acetic acid derivative. Amides that are from acetic acid are called what? An acetamide. Or some people say acid amide. I hear a few people. That's an acetamide because it has the acetyl group on the amine. That's the type of amide it is. Most commonly, you make acetamides using acetic anhydride, or you can use acetyl chloride. Okay, react this with methylamine to equivalence. Which carbonyl do you want to attack?
Top and bottom.
Portion? Top? Okay, well, top. And here, electrons up. Electrons up, that becomes minus. We now have the nitrogen bonded there. What else is on this carbon? Oxygen. And then that is bonded down here like this. Nucleophilic addition to carbonyl. By the way, are we protonating the carbonyl first? Remember we talked about protonating carbonyls? No, there's no acid here. We're not doing an acid catalyzed reaction. We can do proton transfer if you want to be strictly correct, but we're going to bring this back down.
Where did the two H's come from?
Oh, I'm sorry, this is dimethylamine.
Oh,
That means there's two methyls here. Dimethylamine. Bring that back down, kick off the oxygen. Let me come this way. Bring that back down. N, H, methyl with plus charge. That gives that. Because this is cyclic, when the oxygen gets kicked off the carbonyl, it's still bonded within the molecule. See here, when the oxygen got kicked off, it left. Totally left. I mean, this was a leaving group from the carbonyl, but it's still part of the molecule. At this point, we could do proton transfer to go neutral. I reckon I'll come back over here. Should have just went this way to begin with. The final product when we do proton transfer will be methyl, OH. Final product after proton transfer. We made an amide. The leaving group left. This is called kind of bifunctional. We have two functional groups in the molecule as a result of our reaction. Amide and a carboxylic acid. But in terms of mechanism, anything new? Okay.
what do we need the two equivalents for? Is that part of the H plus transfer, or?
Okay.
Or wouldn't
Okay,
it actually
yeah.
take the H and then it would?
Yeah, you see this is an acid.
Yeah,
And methylamine, dimethylamine is basic.
yeah.
See, dimethyl, this is really,
So it would technically take the H, right, and the oxygen would stay minus?
yeah, technically it's going to take the H and you're going to end up with a Me2NH2 plus.
Okay.
Yeah, that's a good point. It's actually a very important point, yes. Because we're making a product under, are we under acidic or basic conditions? This is a base. If you make a product under basic conditions, how's it going to exist?
Basically.
In the basic form. So it's the anion form. To get the proton on here, what are we going to have to do? You're going to have to add some type of strong acid, ACl, sulfuric acid, to get the proton on. Okay, one thing that I will struggle with is when to take shortcuts, when to highlight something. Very important. See, I just sort of showed you the product and was trying to, okay? Yes? Good that you understand that. You need to understand that. As we move forward, though, I will start taking some shortcuts because I don't want to cover points every single time. That's just in the interest of time. There's also just the expectation that, hey, you know this. Shout it out. Yeah. I'll say, yeah, you're right. Here's the other thing. When you get to biochem, all right, they're going to be doing shortcuts all the time. They're going to be doing so many shortcuts, you're like, what's going on here? Okay? You got to realize that biochemists are not organic chemists. All right? So just keep that in mind. So don't freak out when I do a little shortcut because everybody taking biochem in the fall? Who's taking biochem? Everybody taking biochem? You want to take biochem? They don't let you?
No, they don't let us.
Right? In med school.
Oh, it'll be even worse in medical school. Okay? In medical school, they're just going to show you a reaction to product, and they're going to show a mechanism. It's going to look, that's a mechanism? No. Okay? So be prepared for that in the future. And it's okay to say, oh, they're showing shortcuts. I'm going to think mechanistically because that's going to help me understand it better. See, the problem is in biochem, they use a lot of enzymes, and the enzymes, they're magical. Okay? And they just don't show, they're just like enzymes. It's like, wow, that's, okay? Question?
Because if you wanted to get the product that you originally showed, that's when you would do, like now, if you wanted the H on it, you put H plus workup, right?
Yeah. 1 and then 2 would be H plus workup.
Okay.
Totally separate. You can't combine methylamine with H plus or they'll just react. It's like trying to dry your raft while it's in the pool.
Yeah.
No, first swim, then let's dry. Don't try to dry and swim at the same time. You'll just waste a lot of towels. Okay? You'll just waste a lot of acid by adding in methylamine. Okay, the one at the bottom. All right? Everybody do that real quick. That's really quick. What are we going to put on the oxygen? Show the product and then let's talk terminology. What do we do? Because terminology is also important. Popsy, what you got?
I took off the H.
Okay, guys. What you got? Popsy?
I replaced the H.
You replace the H?
I'm not sure if it's the
Terminology, guys. Terminology. Yes, it's important to show product structure. Okay?
Is oxygen the nucleophile?
Yeah, this is your nucleophile here. Acetic anhydride, pyridine. Product's going to be that there plus What type of product did we make? Ester, yes. What did we do to this oxygen?
Alkylated?
And reasonable, but it was not an alkyl. What did we put on the oxygen? Is this an alkyl group?
No.
What's that called? Acyl. That doesn't sound right. Acyl. Yeah. Acyl group. Ketone, carbonyl group. We acylated the oxygen. Acylation. I mean, you could say we acylated the up nitrogens too. To me, it's just, this is more of a relevant term here for some reason. We acylated the oxygen, acylation, not alkylation, okay? We didn't make an ether, all right? Reactivity, use of mixed anhydrides. Why would you want to use a mixed anhydride? Well, sometimes you have to because the acid chloride is not stable. When this is a CF3, that's not a stable acid chloride. So if you want to use this as an acylating reagent, you have to use the anhydride, which is stable and available. Now, since this is symmetrical, you attack either carbonyl, the other one serves as a leaving group. Here, this acid chloride, the acid chloride of formic acid, because if that was OH, it should be formic acid. Everybody's watched the video, nomenclature video? I don't believe that. I can see how many views it's been. I saw 7 views yesterday. I told you that Santa Claus was watching. Okay. The acid chloride of formic acid is not a stable acid chloride. But you can use this mixed anhydride. Now, because it's mixed, we have to assume the nucleophile is going to attack there if we want a bond to the carbonyl with the H. Well, will it? Here's the same anhydride here. Let's look at this. When you have a mixed anhydride, which carbonyl is going to be attacked? Well, that's easy, the more electrophilic one, right? The one that's more partial plus. Okay, well the question becomes, which carbonyl is more electrophilic? On the left or right? What's the difference? H or a methyl? What do you know electronically? What does an H do? Nothing. What does a methyl sp3 carbon do? Donates. So which carbonyl carbon is more electron poor? The one with the rich friend donating or the one with no friends? Okay? Because that donates, there's not as much partial plus here from the oxygen pooling. So yes, this one's more reactive. Indeed, I've used this reagent, and it's very selective for you react here. So the amine reacts here, electrons up. Can I introduce a shortcut? After the electrons come up, then what do?
You kick off later.
Back down, kick that off. All right. I'm going to start doing this a good bit from there on. Now,
Can we do
quizzes.
that on the test?
No, you can't. This is just to save us. If we do this for the next 6 weeks, we'll save probably a whole class period. Then we can talk more about stuff. Okay, we can go over the IR set, etc. All right. You'll see more shortcuts than this in biochem. They'll just, okay? Understand what we're doing. If you have any questions, show it out, draw me. Right, doesn't nucleophile add electrons up, then what's next? They come back down, kick it off. I'm trying to get the product real quick because ultimately we've already learned how to do mechanism. What's the product? The nitrogen's bonded to carbonyl, and what's on the carbonyl? It's an H. Plus triethylamine acetate. We really need to show that out. So you've got to take the H from the nitrogen. If the leaving group takes it, you make acetic acid. But triethylamine can deprotonate the acetic acid, and you can make this. All this stuff, if you just sit down and do out the mechanism, it's all there. Okay, let's finish up. Well, let me ask you to do this one on your own. Okay? This is sort of a mixed anhydride, but it's not exactly an anhydride because this is not just a plain R group. It's a heteroatom. But it reacts as if it's a mixed anhydride. Which carbonyl is going to be attacked? Figure it out, show the product, and then please be looking ahead. We'll move on to chemistry of esters. Please turn in your summary data table this week in lab if you want me to look at it.
Can we include like our percent yield and stuff on this?
Yeah, that's what it asked for. Percent yield, melting points. I would suggest also including literature melting point. Okay, guys.